So first of all, I'd like to welcome everyone. I'm delighted that you could all come tonight, because tonight we're going on a special journey. And we're going on a journey to the bottom of the ocean. And this is a place that actually not many people have been to, and a place to which we actually don't know very much about. So today you're going to be one of the few who's actually going to have this experience. So first of all, let's think about, we need to first of all find a place where we're going to dive, where we're going to dive down to the ocean. And so let's think about our planet. Obviously, could we have the lights down a little bit, Francesca? The planet. We need to find a place now to do our survey. So the first thing we need to know, we're going to dive to the bottom of the ocean. So the first thing we need to know is how deep the ocean is. So how are we going to find this out? The way we routinely find out how deep or what a planet looks like, if you were to go to any planet, and in fact this has been recently done in Mars and Mercury, you take a satellite and you attach a radar to a satellite and you fly around emitting a little pulse. So radar is radio waves, which is an electromagnetic wave, and it bounces off the mountains and the sea, and you build up a picture of the topography. So let's have a look. People have done that for the Earth, and let's have a look to see how it appears. Okay, so this is a map now. What you're seeing here this is a topographic map. So what you're seeing here, the colours here are shaded according to height. So green, sea level here is at 0, are green. Perhaps you can see here we are in the UK, sitting on the European shelf. So as we know, we haven't got big mountains in Britain, and so this is why it's green. Obviously, to the west of us, you go into the Atlantic Ocean, and as you go into the Atlantic Ocean, you start getting into those blue colours. So let's zoom in a little bit on the Atlantic Ocean, Francesca. And you can have a look at similar, perhaps over the weekend, you can have a look at similar maps there's Google Earth and also Google Planets. So actually you can see maps a little bit like this on Google Planets. Right, so let's zoom out a little bit. So we can, that's great. So we're looking, what we're doing tonight, we're trying to find somewhere to dive. So let's have a look in the Atlantic Ocean. So we seem to have quite an interesting looking feature down here. There seems to be, so we know that green is shallower water than blue. So perhaps for our first dive, we ought to choose somewhere a bit shallow. So let's look something quite interesting running down here. So here we have Europe, this is Spain, this is America and Canada. So let's have a little look at that feature. So let's pretend, for example, we were Christopher Columbus, and let's see if we can sail out from Spain from Portugal, excuse anyone, Portuguese people in the audience, and see what we see. So there we are, we've traced Christopher Columbus's steps. So what you see is you're coming off the continental shelf. Here we are in Portugal. Maybe some of you have been on holiday in Portugal. We've plunged into the Atlantic Ocean, and we've come across this rather interesting sort of mountain feature, which is this feature here. So this looks rather interesting. Perhaps we should go and do our dive on here tonight. So we need to find a good site. So let's zoom in a little bit and see if we can find a good place to take our dive tonight. Okay, let's zoom in a little bit more. Oh dear. So when you zoom in, there seems to be a bit of a feature, maybe an interesting crack down the middle of the volcanoes, but it all gets a bit fuzzy and not very clear. Why is that? And in fact, this is a fundamental property, a problem we have with the Earth. This is not because this is bad data. This is, in fact, the best data we have. The problem we have is because of the water. So because these maps are made with radio waves can't travel through water. So in fact, they bounce off the sea surface. And it's actually it's a true fact that we have better maps of Mars than we have of our own planet, which is a bit surprising, really. So if you go, at the weekend, you can actually go into Google Planets and look at Mars. You can see a higher quality map of Mars than of the Atlantic Ocean. So that's something to think about. So why is this? So the radio waves don't go through the water. And literally the water acts as a blanket which makes everything go fuzzy. So what we need to rely on, what we're trying to do is just measure the water depth. It's nothing very complicated, but because the radio waves don't go through the water, they bounce off the top. Although we get a little signature of the topography underneath, it all gets smudgy. So this gets smudgy. In this little diagram, we've got 2 volcanoes sitting here, but we only see one. And here we've got a little volcano, and we don't see it at all. And this is the reason why this map looks all smudgy. And if you don't believe me, you're just thinking, oh, she's not a proper geophysicist, she just hasn't got a very good image. This is a photo. This is an accident that happened in 2005. This is an American military submarine. As you might imagine, they have the best maps of the seabed that anyone on the planet has got. And they basically ran into a volcano, okay, that they didn't know was there. And so this really shows how poorly we know our own planet, and I say the seabed. So this is no good. Let's remember what we're doing today. Today we're trying to find somewhere to dive. So we obviously need to find something else apart from a satellite map to find our image. So we've got no option but to get on a boat and get out there and make a better survey so we can plan our dive tonight. So this is, thank you, Francesca. So this is our sort of our basic premise now. We just want to find out how deep the water is where we're going to make our dive. And obviously this is a very fundamental measurement of the Earth and something that people have been doing for, well, many years. So this is actually perhaps the oldest picture of anyone taking a depth measurement. So what you need to be looking at here, this is from an Egyptian tomb, so 4,000 years ago. And what you need to see is this little man on the back. And he's got a lead weight on a piece of string. And so to measure the water depth, he's reeling the string out until it hits the bottom, and then seeing how far that is. If you wanted to, you could actually do a survey of your own bathtub doing exactly the same thing, and you would find it would take a very long time, and it would be quite tedious to do. However, people carried on doing this measurement as a way of determining how deep the water is for a very long time, right up into the middle of the 19th century. So this was the first ever sort of systematic survey of the Atlantic. This was done for laying the first transatlantic cable. So these days we're very blasé about phoning your uncle in America. You don't even think about it. But back then they needed to lay a cable right across the Atlantic Ocean. And notice they also spotted this little volcano thing, which is the thing we're going to go and have a look at today. Luckily, now that we've, so that's sort of in the past, of course we don't go out now. When I do my research, I could tell you I'm a marine geophysicist and I go out with a big bit of lead on a long string and measure the water depth. Of course I don't do that, because now we have better methods. So rather than using radar, which are radio waves, we use sonar, which are acoustic waves. And acoustic waves, as probably you all know, can travel through water. And you probably know that because you know that whales sing and talk to each other. And that means the sound, the acoustic waves, the noise, travels through the water. And that's exactly what we use now. We use automated methods through using sonar, which were developed at the last, 50 years ago. And we're going to give a demonstration of how that might work today. So what we're going to do in this tank, we're going to simulate us doing a survey. So we're trying to find a nice place to go and do our dive on. And this is what the principle of what we're going to do and how an echo sounder, as these are called, work. So just like the satellite radar, an echo sounder, obviously now we're on a boat, so we need to get through the water, so we need to be on a boat. Oops. And what happens is that the boat lets out a pulse of noise, just as our own system worked. The noise travels down through the water and bounces off the seabed and then travels back. If we know the speed of sound of water, we can measure that time and then we can work out how deep the water is, and we get a measurement like that. Then the boat moves on, lets out another noise, we get another measurement and another measurement and another measurement. So let's see if we can have a go at showing that. So we need a volunteer now from the audience. Well, you were up first, the young man sitting right in the middle. So why don't you come down? Yes. Let's have a round of applause for the volunteer. Okay. Sorry?
I think it's tall enough.
Yeah, I think this is quite big. Okay, great. And watch, we need the thing. And what's your name? James. Okay, James. So fantastic. So, James, we're going to be doing quite a dangerous experiment here, so we need to get you equipped. Can you swim, James?
Yeah.
James can swim. Okay, but nonetheless, why don't you put those goggles on? Okay, and we need you to get into that. Yep. Fantastic. In fact, you're quite nice and tall, James. This is excellent. Maybe you need that as well. What do you think? Okay, so are you ready? You feeling safe?
Yep.
All right, so why don't you go then with Steph and are we ready? So what we've got here, Steph and Karen are here from an organisation called RoboGals. And RoboGals are a student-run organisation who basically encourage girls, in particular, and young women, to come into science and technology. Karen and Steph are going to be running a demonstration outside later, and they do school visits, particularly looking at these sort of Lego sonars that we're going to use. So if you're interested in RoboGals, I suggest you come and talk to them later. Maybe they'd come and visit your school and make some exciting projects with you. Right then, James, so are we ready here? So what we've got here is a Lego boat that's set up just as we had on the diagram with the sonar. Okay, are we ready to go? Are we ready to make the first measurement?
Yeah, so we'll take 3 measurements across the whole line of on the screen. Right.
Okay, do you want to tell, you need to tell Francesca what it is.
Yeah.
Okay. Where's Graham? Where's Graham? Okay, did we get that?
27.
27, okay. Move the boat, is it working?
On the last point.
Where's Graham? Can you do it? Oh. Okay, and the next one? Okay,
Yeah,
that's the last one. How's it looking, Francesca? Did you get the last point?
37.
All right.
Yep.
Great. So let's have a look if that looks about right for the profile that we got. So that does look about right. Okay, and yep. Okay, slight technical hitch, shall we? Okay. Oh my goodness. Okay, so thank you very much, James. That was a great survey. Okay. Okay, thank you very much. Thanks, Graham, I'm sorry. Okay, well, that was pretty successful. So what we managed to do was that we surveyed that surface, and we seem to have found something rather interesting. So perhaps this is going to be the site of our dive tonight. So now let's think about, okay, so we found a good place to go. We're going to be in the middle of the Atlantic. We found a rather interesting sort of erupting volcano, and so this is where we're going to go. So how are we going to get there? This is one of my personal heroes. This is called a chap called William Beebe, and he held the deep diving record. So he dived to 1,000 meters in 1932. And this is way before there was any health and safety. He didn't know what was going to be down there. He just dived down there. And what he reported, people actually thought he'd lost his mind. And in fact, you're going to see exactly the same things that he saw later in a moment. Whoops. Okay, today, so he was in a big diving bell attached to a cable. But of course, today we're going to use a more modern system. So let's have a look at how we're going to make our dive tonight. Okay, so obviously we're going to steam out into the middle Atlantic. So we're going to go on a boat, and it's going to take us about 5 days. So we're going to get on in London, and we're going to sail out for about 5 days. And here comes the vehicle that we're going to go down to the bottom of the sea in. And it's a deep diving submersible. So, you know, military submersibles, they don't go very deep. We're going much deeper than anyone normally goes. In fact, fewer people have been down as deep as we're going tonight than has been into space. So we need a special submersible. And there are only 6 in the world that can go to the depth that we're going to. What we're seeing here, then, this is the Scientific Submersible. And so it's got things like lights and cameras. Oops, and let me just show you over here on the diagram. What we saw there, we saw lights and cameras. We saw the big sample. So you saw this bit coming out of the hangar. Obviously, we're going to down there, maybe we'll find some rocks, maybe we'll find some animals. We're going to collect them and put them in our sample bag. Perhaps what's most important for us as people is where we're going to go. So tonight, it will only take 3 of us. So it's going to be me, the pilot, and each one of you. So 3 of us in the capsule. And here's the capsule, and this is a sphere. So it's going to be quite cramped. We're going to get quite friendly with each other, and we're going to peer out of a porthole each. It's a sphere, and this is very important. It's very important because we're going to have high pressure as we go down. So we're now just going to do a little experiment just to show how important having a strong cylinder to hold us in by doing a little pressure experiment. Thank you. So we need another volunteer for this, but we thought perhaps we ought to have a mum for this. There's a fantastic looking mum over here. So sorry about that. We have health and safety protocol guidelines. Thank you very much. Yes, we're going to have a fan, so I just don't want your child to be anywhere near it, okay? So, yeah, you better go and stay with your dad. Or you can stand here and watch, okay? Okay. So your name is?
Sally.
Sally, all right then. So Sally, let's Okay, Sally, so are you ready to drive this? And one of you. Okay, Sally, so what Sally's going to illustrate for you is differential pressure. Okay, so Sally's going to take a tin can . If we can light the gas.
There you go. Come up here to the...
God, it's getting really dangerous. Graham, what's going on?
The nozzle flying up.
Does the project make noise?
Flying up. I can't believe it.
What's happened?
Nozzle's flying up. There you go.
All right.
Oh, your hand.
All right. All right, so let's get started. So Sally,
Yep.
Sally, what we need to do then is first of all to get you practice, okay? So Sally, what we need you to do is you're going to heat the water, and then you need to plunge it upside down into the water like that, okay?
Nice.
So we need to practice. On my count, yeah, okay, so are you left-handed? No, you're going to be this way up. Are you right-handed?
I'm right-handed, yeah.
So maybe you want to hold it like this,
Yep.
and you're going to heat it, and then you're going to go like that.
Okay.
Okay? So Sally's going to practice now, okay? After him. No, don't heat it yet. 1, 2, 3, into the water. Right, a bit quicker, Sally. Okay, and let's go. 1, 2, 3, go. Yeah, that's more like it. 1, 2, 3, go. Okay, so let's get you loaded up. You've got the water. No, okay, no, water out. Okay. So at the moment, what this is experiment about is it's all about pressure. Okay, so at the moment we're at 1 atmosphere of pressure. So the can is open and it's got 1 atmosphere of pressure on the outside. And of course the top is open, so it's got 1 atmosphere of pressure pushing out, just as we would be in our submersible bubble, which is why the can is completely at rest. Now Sally's heating up the can, and we need a nice head of steam. Really good head of steam. A little bit longer, I think. Because you see some steam? Do we see enough steam? It needs to look like a steam train. Perhaps our gas is... what do we think? Sorry, need a bit of build-up. Oh. But if it doesn't work, it doesn't work. All right. A little bit more steam.
Yeah, steaming.
Is that enough? Is enough? All right, so should we give Sally a countdown from 10? Yeah, as quickly as possible. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go! Oh! So what happened? My goodness, you want to show everybody? Okay. And can you get the fish off? Big fish off. Wow. So what happened there? My goodness. So thank you very much, Sally, you beast. So what happened there? There was some water. Is Sally just an amazingly strong woman? Is Sally an amazingly strong woman? No. And if you actually look at the shape of that, it's not that she squeezed it. What happened is that we had a bit of water in the bottom, which we heated. Okay, and as we heated the water, it became steam. Okay, and that pushed the air out of the can. Okay, and while the steam was hot, everything was fine. But then what happened is she tipped it very quickly and very professionally, I might say, into the water, and she closed the top. Okay, and then the steam became cold and went down to droplets of water again. But the air couldn't come back in to replace the pressure, so we ended up actually with a partial vacuum in the middle. Okay, so we had low pressure on the inside, high pressure on the outside, and that's why the can collapsed. Okay, because we had differential pressure. And that's why we're going to go to the seabed tonight. That's why having a very strong capsule is so important to us, because obviously it needs to be strong enough. The can isn't very strong, but obviously if we're in a nice cylinder, and this is we're made of titanium, it's strong enough to hold the differential pressure as we go down. So thank you very much. Okay, so we've now learnt about differential pressure, and we've seen the submersible. Now I'm going to give you a test as to how well you know about what we're going to do tonight. So you've noticed in front of you, you've got 3 cards. Okay? Yeah, I know, sorry. I know.
Want to play later?
No, I know.
What?
No, let's just
Skip it?
play it. Can you play it back to back?
Well,
Okay, maybe I play it. Maybe I play it. Should we play
I
it?
can play it while it's
Yeah, okay.
up to you.
Okay, well, maybe I should... No, let's do the quiz.
After the
No, I'll do it after the quiz. All right, then, are we all ready? So let's see how much attention you were paying. Okay, so this is the scenario, okay? We're out on our research vessel. We've now arrived at the dive site that we found in our sonar experiment. So we're ready to go. So you're going to come in the submersible, so I need to make sure that you've been awake and that you've been understanding what we're doing tonight. So what you're going to see is multiple choice questions, and I want you all to see how good an audience you are. So let's have a look at the first question. Okay? The first question, we're going to dive down to the sea bottom. How far are we going to go? Okay. Oh. Okay. Well, all right then, let's see how that went. All right, so let's see if you're right. So a lot of people went for C, and actually, I don't know how to do this. A lot of you went, okay, should we have some quiet then? Let's hear the answer. All right then, so a lot of you went for C. Can I have more volume on this? And let's see if you're right. Oh, all right. Can you go and ask them if I can have more volume on my mic? I can't, you know. Who do we say? Okay, because I can't hear me. All right, so those of you that got, all right then, those of you that guessed, quite a lot of you guessed C, and in fact you weren't totally wrong. In fact, the deepest ocean on Earth is 10,000 meters, but that's actually at a subduction zone, a deep trench. We're going on a mid-ocean ridge, a volcano that sticks up relative in the sea. So the correct answer, quite a few of you got B, so well done to everybody who got B. We're going to travel today 2.5 kilometers. All right, let's move on. Let's see what the next question is. This should be quite easy. All right. Yes, okay, so that was quite, yeah. We haven't practiced this bit, had we? All right, so very good. I know. I don't know how. No, I know. All right, so that was well done. Most of you got that one right. All right. So here's a more difficult one about pressure. No, you're not allowed to hold up all 3 letters up the back. That's really not, only one. There's definitely cheating going on. So question 3. During our dive, and don't forget we're going a very long way down, 2.5 kilometers, what's going to happen to the pressure? Okay. All right, and let's see. So, it wasn't like this at dress rehearsal. It's a Christmas tree. All right. Oh, very good. Okay, so it's very, very important. What you're going to learn, we obviously live on the surface of the planet, and so pressures don't change very much. And actually, your body is actually full of air cavities. So you've got your lungs, and you've got some other air cavities, and that makes it very, very important that the pressure stays the same So in other words, if the pressure didn't stay the same, we would collapse. And in fact, you're going to see some very special animals tonight who are specially adapted to live in pressure, and they do that by not having air pockets inside them. So it's very, very important that our capsule is going to stay at the same pressure. All right? Is it going to be light? Are we going to see sunlight all the way down to the seabed? What do you think? All right, very good. So, excellent, that was about 50-50. Okay, so you need to remember this when I start showing you the picture of the animals. You need to remember this. This may have been a mistake. Okay. Is it going to be cold? Sorry? Is it going to be cold at the bottom? What do we think? What do we think? Okay, a bit mixed. Is it going to be cold? Oh, okay. All right. So we've got 2 more to go. Okay, how long do you think it's going to take? Is it not working at all? Alright, this is our last question then. Our last question. Yes.
Okay.
All right then. So let's see. We've now done our briefing. And let's say perhaps the most important issue there was the pressure. At all? At all? Who's got a microphone? The microphone isn't working. Right. Okay, thank you. Is that working? Oh, that's much better. Okay, that's why we had very little control there. All right. So let's play the. Can you go back? Yeah. Okay. Oh. All right, and let's see now. Then we're now ready to go on our dive. Let's get in the submersible. So this is the people who are going before us. This is a friend of mine, Susan Humphreys, who's getting in now. And you can see how close and claustrophobic it's going to be in there. We're going to be in there about 8-9 hours. So you better make sure you've gone to the bathroom before we go. And it's going to be, it's going to be quite cosy. So here's the submersible all ready to go. We're closing the hatch because obviously it's very important to us that we keep the pressure in the diving sphere strong. We're each going to have a porthole, just one porthole to look out. And the size of the porthole, they're about the size of a dinner plate, but actually because the glass is very thick, as you might imagine, you feel a bit like you're sort of looking through a saucer. So it's quite hard sometimes, quite frustrating as a scientist. You start things that you want to measure or go and collect, and you can't really quite see them. It's like wearing, just like being underwater, it's like we're having thick glasses on, so it's quite hard to see. And so here we go, coming down into the water. A little bit lower, a little bit lower. We've got people standing by in case we have an accident as we get into the water. And here we go, and we're in. All right. Okay, we're going to play the next one. Yeah. It's very fun. The animals. Yeah, I'm going to start. All right, so now we're ready. We're actually going on our dive. We're just going to see the submersible coming down a little bit. And what you need to imagine, so there's 3 of us in this bubble. I've got a window over here, and you've got a window on the other side. And I'm going to show you what we're going to see through the window. So first of all, let's just see the sub. Here we go. So we're actually doing a free fall descent. We're going to be descending at 30 meters a minute as we go down. And we're going to see all sorts of animals living in the water column as we go down. And you need to remember, just to emphasize this, that fewer people have done this, what we're doing tonight, than have actually been into space. And that's not an exaggeration. So it's a very, very special experience. Okay, so what you're seeing here, so here's your porthole, and you're looking at the depth axis here. So this is, as we go down, you're going to see this thing slide down. So here we are at the surface. Obviously some seals have come by to interact with us. And of course we're all very familiar with what happens in the near surface. Okay, oh my goodness, hold it there. So as we learned about the sunlight, so sunlight is going to be one of our main drivers. And in fact, sunlight, as you probably all know, the ecosystem that we live in is all driven by photosynthesis, by plants. So you may not like cabbage, but actually it's the green plants which are the whole reason that you can live. When you go into the water, the sunlight becomes so dim that after about 100 meters, there are no plants at all. And in fact, that's why these images look so crystal clear, and that's because there's no plants, there's no photosynthesis. And so it's starting to get dark and dingy. And so the first thing that happens to animals is that they start to go transparent. Because what are the animals down here going to eat? Okay, there are no plants. So all they can rely upon is bits of food that maybe float down from the surface, or they're going to eat each other, okay? So being transparent is quite a good method to hide from any animal that might try and eat you. So let's go down a little bit further. So the first animals, as I say, have gone completely transparent. And keep your eye on the depth gauge. We're going down. Basically, we're going down as we go down. So here's a very funny little squid. Okay, and he seems quite interested in us, really. Okay, and don't forget, here we've got the lights of our submersible are now turned on. So these are not generating light, these are just, they're catching in the headlight. Oh my goodness me! So what was that? Okay, so we're now a little bit deeper, okay? We're now at about 500 meters, okay? And so these animals, sorry, let me just show you this slide over here. These animals, they're basically not really, although the pressure is increasing significantly, they're not that worried about the pressure because, say, they have soft organs inside. They're really worrying about the light. And so the light is now getting really, really dark. And so one strategy is to have great big eyes so that you can see other animals and eat them. Okay, so this is what's happening now to about 50 meters depth. And this is exactly what you'd see in our submersible. We've now got animals with big eyes because it's getting very, very dark. Right, let's carry on and see what else we're going to see. Whoa, and there's another one. Oh, my goodness me. All right, my goodness me, it's now getting quite scary. So we've gone down even deeper now, okay? So now it's actually gone very, very dark indeed. And what happens, the reason why sea looks blue is because it reflects blue light. And so by the time we got to this depth, in fact, all the red light has been absorbed by the water. So a lot of animals are starting to become red, because if you're red, you look completely invisible at these sort of water depths. Note that the animals here, they've given up trying to have big eyes. They can't see. They're just fumbling around in the dark. It's completely pitch black. There isn't much food down here. And there isn't much food, meaning that you've got to be kind of aggressive, I'm afraid. It's a fish-eat-fish world down here. And so this is a particular example, and we've got a very fine specimen that I'll show you at the end of the video. So here we've got, I say, it's a red, and he's called a deep-sea anglerfish. So he's got big teeth because I'm afraid if he sees you, he's going to eat you. Let's go down a bit further. Okay, we're now going down. This is sort of, oh my goodness me, that's another funny little fish. When we get down to about this depth, then the animals start making their own light. So there's no sunlight, no light at all here. So rather, the animals here, in order to either find a mate or find something to eat, they start making their own light. So we're getting down to the bottom now. Remember, we're going down 2.5 kilometers. We've got nothing. Oh my goodness. And here we are at the seabed. Okay, and everywhere, oh my goodness, this is called a Dumbo elephant. I mean a Dumbo elephant, Dumbo octopus. Okay, thank you. Okay, so I managed to recover some specimens from the Natural History Museum. So my friend Adrian Glover from the Natural History Museum has lent you some specimens here to show you. And you could go and have a look at these. I don't know if these are showing up. Are we seeing these? Can we see these? I know you can. That's not really focusing, is it? Okay, the light's not good. No, you can't see it, can you? No? No, okay, can we have the lights back up then? We won't, maybe you could come down and have a look afterwards. So this is known as a giant scale worm, and he scampers around the seabed. He was actually found at about 1,000 meters depth, and he has these fantastic, you can come down and see him at the end of the lecture. So he has these fantastic bristle features, which actually also help him with respiration. Perhaps the star of the show is this one. This is one of those deep-sea anglerfish that we saw on the video. So I don't know, it's a great shame that you can't see him. In fact, can we really not? It's really not possible to see him. Okay, so he's found at about 1,000 meters depth. Maybe Lisa could come and hold it for me. And what you'll see, so he's one of these very aggressive animals, and he has this light on the top. Okay, and as you see, he's quite a round, he looks a bit like a ball. So he's actually a very lazy fish. He's got very small fins, and basically he lives in the pitch black, so he can't hunt anything. He just sort of floats about. And if any animal comes near him, you might see he's got great big teeth, and actually he has the ability to eat something that's twice as big as himself. Okay? And I would say, when I was a child, my brother was a bit like this. Float around, and if something came along, would eat all of it. And I say he's very characteristic in that he has a little light on his top that he generates through bacteria, and this is how he attracts animals to come and see him. This is a female fish, and I'm sorry you can't see him here, but this is a female fish. And in fact, her mate is the little thing down here. So this is actually the male fish. So you can see the female fish is the aggressive beast. We have a female theme tonight, and the fish is doing exactly the same thing. So this is a deep-sea anglerfish, and you might want to look at these on the web, and I must say, this is the first time I've ever seen one myself as well. This is from the Natural History Museum, and I always thought they were enormous, but actually she's a very fine specimen. So you could, by all means, come down and have a look at that at the end of the lecture. Thank you, Lisa. Okay. So now we've arrived at the sea bottom, okay, and we've found our volcano in our survey, and we're now going to look around and see. We've seen all these animals on the way down. Let's see what's happening on the seabed. Okay, so these really remarkable features are known as black smokers. So don't forget, we're now 2.5 kilometres down. The light, it's all pitch black. What we're seeing is the lights from the submersible. So imagine you're looking out through your porthole, and it spawns all this fabulous life. And these were a big surprise when people first discovered it. People were hugely surprised by them. Could anybody guess how hot the steam is in this coming out of this smoker? Could anybody give me a number? Okay, some answers there. Oh, it's on the. Oh my goodness me. Okay, you were cheating. There were some very accurate answers there. Okay, so you can see it here. It's on the slide. It's actually coming out at 350 degrees C. So how hot is that? Well, that's hot enough to melt, certainly hot enough to melt our submersible, and hot enough to melt a lead pipe. And so when people first discovered, they've only known about these for 30 years, which isn't very long ago, and they actually account for 25% of the heat that escapes from the Earth. And so it was a huge surprise, and I say only a very privileged few people have actually seen them. Thank you. They're black because they're full of metals, so they're full of copper and iron sulfides. And what happens, don't forget, we're on a volcano. We have a heat source, and this little diagram illustrates what's happening. We have a heat source, which, don't forget, we're under the sea, so we've got water down here through the fractured rocks. The water heats up, becomes steam, and shoots up to the surface to make these discharges. As it shoots up, then it draws more water in from the sides. And this ecosystem, don't forget, we've got no photosynthesis here, we've got no sunlight, so all these animals, so I've just decided to say that as a bit where there aren't any animals, but they're all living on the chemicals, the metals that come out of the Earth. And this is the only ecosystem on the Earth that does this. And you can see it supports quite complicated animals. So we've seen some very exciting looking fish. This is kind of a boring little fish. This is an eel pout. All the animals down here are like, whoa, my goodness me. What was that? So this is actually one of my favourite animals from these vent fields. This is called a Pompeii worm. And our friend the Pompeii worm holds the world record for living in the hottest water. Okay, so he can live in water that's 80 degrees C. So that's, if you think about making a cup of tea, that's just about the temperature that you pour the water out of the kettle onto your tea bag. And here is the Pompeii worm living in this hot water. Thank you. This is the only ecosystem we know that is living on chemicals, and they're all reliant on little bacteria which synthesize the metals coming out of the Earth. And in fact, people think that the earliest, when Earth started evolving on the planet, it may well, back at the beginnings of time, before we had a proper atmosphere generated on the Earth, that they actually may have looked just like this. They might have synthesized metal sulfides, coming out of the planet. This is another very distinctive, and so there's another nice displays of this in the Natural History Museum. This is called a tube worm, and these things can be about 3 meters long. What's interesting about them is that this red colour is actually hemoglobin, which is the same molecule you have in your blood, but here they're not exchanging oxygen and carbon dioxide, they're actually exchanging metals from the surrounding water to help feed the bacteria that they're symbiotically living with. Thank you. So as you might imagine, this whole ecosystem, I say, was not known, and it's led to a lot of potential, perhaps, for biological, medical research, and also the origins of life. And perhaps life on other planets might, well, if they haven't got oxygen in the atmosphere, they might well look like that. This is now a white smoke, and I've got examples of these smokers on the table for you. And this is just a little bit, you've got the white smoker here. This is just slightly lower temperature. And it's just slightly lower temperature, so it's not picking up the metal oxides. The metal oxides, the dissolution of the metal oxides depends on the temperature. So if the temperature drops a little bit, it becomes white because it becomes chemical minerals like barium rather than copper and iron sulfide. Okay, and that's just the rest of the sea that we're seeing. So let's have a look at some of these specimens. So sorry, the cameras aren't working very well, so we'll see how we go. So this is a piece of chimney. So you saw lots of these. It's quite heavy. It's made of metals. And this can grow about, this much could grow in about 20 days. Okay, so as all the metals spew out, and that's really quite quick. If you think about how quickly a plant grows, that's growing quicker than a plant. This is a section, I'm sorry the cameras are so, do you hold that one? This is a section through one of the, yes, I need that. Yes, okay. This is a section through one of these chimneys. I say this is meant to be, again, from the Natural History Museum from Richard Harrington. And what you're seeing, if you want to come up later, we're actually seeing different chemicals. So we're seeing chalcopyrite, which is a copper iron sulfide, which is the highest temperature mineral here, which is the yellow mineral. And then as the temperature of that cools down in the chimney, then we're getting lower temperatures, so these greys, sphalerite, the white is anhydrite, other sulfides, other metals are precipitating to give us this banded, so this is a section through one of those chimneys. Thank you, Tanya. Okay, so that's shown us the hydrothermal vent fields. I can't emphasise, people didn't know about these until 30 years ago. And it actually meant that all of our budgets for how the Earth is cooling down were all completely wrong. Okay, so let's carry on a little bit more and have a look what else we're going to find. So don't forget, we're basically diving here on a volcano. Okay, so the oceans take up 70% of the planet. All of the oceans are floored by basalt. That's this rock that you're seeing here. So volcanic eruptions must be very common, and yet we've hardly ever seen them. And in fact, the times we most see them is when there's been an accident. So this is actually a geophysical instrument that was left on the seabed, and unfortunately an eruption came along and trapped it and caught it up. And so we had to send a submersible down to free it and release it. So this just shows us that all of this seabed, so don't forget 70% of the Earth floor, the surface, is made of this rock called basalt. Okay? Let's go on then and see an eruption in action. Okay, so what you're seeing here, this is known as a pillow basalt eruption. Okay, and what's happening? Don't forget the water. We know that the water is quite cold, so the water's only just about freezing. The magma coming out here is at about 1200 degrees C, so it's very, very hot. But it cools very, very quickly to make this crispy skin. And that's because the water is cold. But then because the magma keeps flowing, it sometimes spews out and bursts out to make this distinctive pillow shape. Okay, and these are known as pillow basalts, and so every time you go over the ocean, this is actually what pillow basalts are made of. This is a section, so I'm going to show you two things about volcanic rocks. So obviously I'm from an earth science department, although I'm a geophysicist, which means I take remote sensing measurements. Of course, ultimately we're looking at rocks, and so I want to teach you two things about rocks today. One is about crystal size and how things cool, and the other one is about bubbles and eruptions. So what we saw there, we saw magma coming out of the ground at 1200 degrees C and chilling very quickly as it went into the cold ocean. This is a piece of that rock that's now on land, and perhaps you can see around this is one of those pillows that's then cooled. Perhaps you can see it's got a dark black rim all the way around. Can you see it? Good, Daniel can see it. So Daniel can see it, we can all see it. And this is just because it chilled. So this is the edge, that skin that formed, just like skin on a custard. whereas in the middle, the rocks in here cooled a little bit slower, and they've got bigger grain size. So that's the first thing that's going to change the type of the rock. The second thing that's going to affect how things erupt is to do with bubbles. So as magma comes out of the ground, don't forget we're on a volcano here, and magma is going to start rising. Magma often contains things like water and carbon dioxide, and as it comes up, it starts to form bubbles. The bubbles, because they're full of gas, they want to rise, just as we're seeing here on the diagram. So they have a sort of buoyancy, they want to come up. But of course they've got to travel through the magma. And so there is, the forces that are acting on them are the buoyancy to make the bubble come up, and then the most important force is the viscous force. So this is the drag force, it's how hard it is to get through the magma. Okay, so that controls how quickly a bubble is going to move. And in the reality, we tend to have two different types of magma. Magma can usually, it depends on what the chemical composition is, but you can be runny, and if the magma is runny, then the viscous resisting force is slow, and so the bubbles travel very quickly, they start to crash into each other, and they make big bubbles, and they just rise up to the surface, and pop out without causing any trouble. If you've got a very sticky magma, then the bubbles travel very slowly and they start making a foam. And let's see what happens to an eruption if we've got a sticky magma. So if you remember the last video sequence, we just had lots of steam and we had the magma rushing out, but there wasn't really anything much happening. Whereas here we've got explosions. And all that the difference is this is now sticky magma, so highly viscous magma, and all the bubbles are now caught up. They can't sort of just drift out to the surface and degas. They're all forming a foam, and that's what's giving you explosions. And you get exactly the same thing. These are obviously pictures from underwater, and these are very rare videos of underwater eruptions. The same thing happens on land. So, for example, you've got Hawaii, where everything just comes out nice and gently. And then you think about Mount St. Helens. Maybe some of you remember when Mount St. Helens erupted. With lots of violence, we've got bits of magma spewing out. And the only difference is that this is a thicker magma, and it's full of bubbles. All right, so why don't we see if we can simulate that in our final demonstration. Okay, we need another volunteer. Oh. Yes, let's have it. Do you want to? Yes, come on, why don't you come down? Okay, why don't your friend come down as well? Why don't you come down as well? Because I want to show you, let's just show, why don't you come over here? Sorry, what's your name? Peter. Okay, Peter. So this is, I'm going to show you two different rocks. So that was the first rock. How heavy is that? Do you want to tell the people? Okay. And this would be our bubbly magma. How heavy do you think this is?
Quite heavy.
Quite heavy. Oh. It's very light. And why is it light?
Because it has holes.
It's full of holes. Okay, so this is a pump. Right, exactly. Well done, Peter. Okay, thank you. Okay, so let's see. We've seen it in the box. Let's see if we can do this in the experiment. All right, are you ready? So what's your name? You're a reluctant volunteer, perhaps. All right then, Mary. So what we've got here, we've got two fluids, okay? We're going to try and simulate the viscosity experiment. So first of all, we've got pure mineral water, which should have a low viscosity. Okay, so let's see what happens. We're going to pour in salt. This is just to get the bubbles to nucleate. Okay, can we see what's happening? Okay. Can you all see that? You know that? Okay. So that was quite a gentle, quiet sort of eruption. Okay. So now you're standing well back. So now we've got the Coca-Cola, okay? And as you all know, Coca-Cola is full of sugar, and that makes it more viscous and more sticky. So let's see what happens if we do exactly the same thing with the Coca-Cola. Oh my goodness, so can you see that? So now it's made a big frothy mess, and it made a big frothy mess because the Coca-Cola was so viscous, the bubbles couldn't crash out and get out very easily, so it made a big foam and a big viscous eruption. Thank you very much. So that's the end of our dive. We've been down for a long time now. Remember what we saw? We saw all those animals as we dived down. We saw those hydrothermal vents and we saw those volcanic eruptions. It's time now for us to get back to the surface, so let's go back to the surface and reflect on what we saw. If you were to do a survey, so we just did a little survey, a little two-dimensional survey over our volcano. This is what the data really looks like. So this would be a survey that you might undertake. And what you find is this volcano where we went to tonight is a very long, we sort of saw it on the first image, it's a very long, skinny chain of volcanic activity. And so if this volcano was actually to erupt, we're only looking through our little porthole. What would really happen if one of these, we know that all of this rock over here is basalt, so how does this system really erupt? And what would happen is that actually when an eruption happens, we've just been unlucky, we've actually never seen one, which is just shows you how remote and how little we know. So if one of these things failed, basically the whole segment would erupt, the magma would come up from the magma chamber and spew out onto the seafloor. But unfortunately, probably neither me nor you, well you might be lucky, but probably definitely not me, is actually ever going to see one of those. So how do we know this? So we know it partly from dating the rocks, but perhaps the best place we could go to actually see this process would be to think a little bit. So tonight we went diving about here, didn't we? Just off Britain. Here's England. If you trace the mid-ocean ridge up, you'll find that it slips up onto this island, which is Iceland, okay? So Iceland is actually just part of the mid-ocean ridge system. And so, of course, we all know that we have eruptions on Iceland. In fact, there was a very naughty volcano 18 months ago, you may remember in the news, called Jökull, which did exactly that. And so let's imagine, okay, we're probably not going to see an eruption under the sea, but we can see an eruption, this is our last video now, eruption right up here on Iceland. And let's remind ourselves what it looked like. Alright, so exactly that. So for scale, what you're seeing here, here's a road, and so this is what we think happens under the sea. So we've got a whole great big segment. This is why, if you remember anyone who was travelling on a plane, all the planes were grounded because of all the ash in the air. Of course, when we're under the water, the ash wouldn't be coming out, but nonetheless, we think that when a segment actually goes, it would cause as much disruption under the water as if we've just been unlucky that we've never seen one. Sometimes we put down sensors to try and sense, because obviously as one goes, we're going to get little earthquakes, but basically we've never managed to record one and get out there and watch it. So actually, we're often reliant on using analogies by looking at Iceland. And I say, although this was a very big inconvenience last year, 18 months ago, it nonetheless taught us a lot about how the mid-ocean ridge volcanic system works. Okay, so let's accept that most of us are not going to see a volcano. So tonight, then, for our finale, let's see if we can make our own volcanic eruption. All right, so I want to ask, is it anybody's birthday today? Okay, come on down then. The chap who's... No. Okay, everyone, so this is... Okay, everyone, so this is Bartek, who is 15 today. And he, for your delight and entertainment, is going to set off the volcano when my glamorous assistants have so primed. All right, are we ready then? So you want to hit the big button, the green one. Okay. Oh. All right, and what's happening? All right, sometimes when a volcanic eruption is going to happen, nothing happens for a bit. And actually, it's why it's very dangerous. A lot of volcanologists have been... Sorry? You want me to look? You really want me to look? I should have my glasses.